Have you ever wondered how the absolute biggest tech platforms on the planet survive massive, catastrophic hardware failures without losing a single byte of your data? Like, when a server literally goes up in smoke, how does the system not just survive, but just keep on running without a hiccup?
Well, welcome to this explainer. We're taking a deep dive into the frankly fascinating world of distributed systems. Today, we're breaking down the core concepts from Chapter 6 of the System Design Interview Guide by Alex Su, and we're focusing entirely on how to design massively scalable key value store from scratch.
Okay, let's dive into this. Here is our roadmap. First, the CAP theorem dilemma. Then, partitioning with consistent hashing. After that, replication and quorum consensus. Fourth, resolving conflicts with vector clocks. And finally, detecting and handling failures.
Section 1. The CAP theorem dilemma.
So it's a pretty simple fact. Building a key value store for just a single server, it's easy. You can compress the data, you can keep the frequently used stuff in memory, and leave the rest on disk. But honestly, even with all those clever optimizations, a single server is going to hit its capacity incredibly fast. To support real big data, we absolutely have to distribute it across many servers. But the moment we do that, we have to play by a very strict rulebook.
Now, what's really interesting about this rulebook is it's actually known as the CAP theorem. It mathematically proves that a distributed system can only guarantee 2 out of 3 things simultaneously: consistency, availability, and partition tolerance. Let's break those down real quick.
First up is consistency. This simply means that every single client sees the exact same data at the exact same time, no matter which specific server node they happen to connect to. It's basically your baseline requirement for absolute accuracy. Next is availability. This means that any client requesting data is going to get a response, even if some of the nodes in the background have totally crashed or gone offline. Basically, the system always answers.
And finally, we have partition tolerance. A partition is just a communication break between 2 nodes. Because network failures are, just an unavoidable reality of the physical world, a distributed system must be partition tolerant. So the crucial takeaway here is this. Since we have to have partition tolerance in the real world, we are forced to choose between consistency and availability when a network break actually happens. You literally cannot have both.
Section 2, partitioning with consistent hashing. Keeping those CAP theorem trade-offs in mind, let's look at how we actually break up massive data sets. And we aren't just talking about abstract theory here. The technique we're about to explore, consistent hashing, is the engine behind some of the most robust systems in the world. It powers Amazon's Dynamo database, Apache Cassandra, the Discord chat app, Akamai's content delivery network, and similar concepts drive massive architectures like Redis and Google's Bigtable. But when we split data into smaller partitions, we face 2 huge challenges. First, we have to distribute the data evenly, so no single server gets totally overloaded. Second, and this is the tricky part, we need to minimize data movement when servers are added to scale up or removed because they crashed. The solution? It lies in this concept called a hash ring. Instead of a traditional table, servers are logically placed on this ring. When we have a piece of data, let's call it key 0, it's hashed onto this exact same ring. To find out which server gets the data, we just move in a clockwise direction from the key's position until we hit the very first server. As you'll see, key 0 maps directly to server S1. The beauty of this is if we add or remove a server, only a tiny fraction of the keys on the ring need to be moved around, rather than reshuffling the entire database. It's a real game changer. Section 3, replication and quorum consensus. So now our data is partitioned, but we still have that inevitable problem, node death. How do we ensure our data survives if server S1 just suddenly catches fire? Well, we replicate it. We copy the data to multiple distinct servers. But obviously, replication creates a synchronization nightmare. To keep the data consistent across these copies, we use a formula called quorum consensus. It relies on 3 tunable parameters: N, which is the total number of replicas, W, the number of write acknowledgements needed, and R, the number of read responses needed. Basically, if W plus R is greater than N, strong consistency is guaranteed, because there will always be at least one overlapping node with the latest, most up-to-date data. And this brilliantly illustrates how that balancing act works. Imagine a coordinator acting as a proxy between the client and the servers. Let's say N equals 3, meaning the data is copied to servers S0, S1, and S2. If we set W to 1, it doesn't mean data is only written to one server. It just means the coordinator only needs to wait for an acknowledgement from one of those servers before telling the client the write was a success. Tuning these parameters is a delicate balancing act between latency, how fast the system responds, and strong consistency. Section 4, Resolving Conflicts, Vector Clocks. Now, what happens when things happen at the exact same time? We absolutely need a way to resolve data collisions. Imagine a scenario where high availability is prioritized over strict consistency. A user updates their name. Server 1 processes an update changing it to John San Francisco, while at the very same millisecond, Server 2 processes an update changing it to John New York. The system now has two conflicting versions of reality, and no simple way to know which is the right one. To fix this, we need a versioning system to track the exact lineage of the data. Enter vector clocks. A vector clock simply attaches a server and version pair to a piece of data. If server X writes the data, it either creates a new entry for itself, or it just increments its existing version counter. By looking at these counters, the system can mathematically prove whether one piece of data is an ancestor of another, or if they're in direct conflict. Let's move to this example and see how this builds in practice. A client writes a data item handled by server X, creating version D1. Server X updates it again, creating D2. But then two different clients read D2 and update it simultaneously through different servers, Y and Z, creating D3 and D4. These are sibling versions, a conflict. So the next time a client reads the data, they get both D3 and D4. The client application itself resolves the conflict and writes back the reconciled data, resulting in D5, which correctly logs the history of all three servers. Pretty clever, right? Section 5. Detecting and handling failures. We've partitioned, we've replicated, we've resolved conflicts. But this brings us to the final piece of the puzzle. How does the system actually know when a server has died in the first place? In a massive system, you can't just have one master server checking up on everyone. That's a single point of failure. Instead, we use a decentralized method called the gossip protocol. It works exactly like a rumor mill. Every node keeps a membership list and a heartbeat counter. It constantly increments its own heartbeat and sends it to random neighboring nodes. Those neighbors update their lists and pass the rumors on. Oh, and to ensure replicas stay in sync in the background without sending massive amounts of data, the system uses cryptographic structures called Merkle trees to quickly compare and repair any inconsistencies. To put that into perspective, imagine node S0 checks its membership list and notices that node S2's heartbeat counter has stalled at 9908 for a suspiciously long time. S0 sends this rumor out to random nodes. Once multiple independent nodes confirm that they also haven't heard from S2, the system officially marks S2 as down. The system then dynamically bypasses S2, ensuring that client requests are seamlessly routed to healthy servers on the hash ring. And that brings us to the core philosophy of designing systems at this incredible scale. As Alex Shu points out in the text, failures are not only inevitable, but common. Great engineering isn't about trying to build a perfect machine that never breaks. It's about intelligently anticipating that every component will eventually fail and designing a system so resilient that the user never even notices. So I'll leave you with this. If you were designing a massively scalable system right now, are you building to prevent failure, or are you building to survive it?